I welcome you all for this presentation on Introduction to Satellite Communication. So these are all the contents of this presentation. Introduction to Satellite Communication, Kepler's Law, Newton's Law, and you can see a few orbital parameters. As we can start with the first one, that is Introduction to Satellite Communications. Satellites are specially made for telecommunication purpose. They are used for mobile applications such as communication in ships, vehicles, planes, handheld terminals, and for TV and radio broadcasting. They are responsible for providing these services to an assigned region on the earth. So we have to assign some region to a particular satellite, and this satellite will provide service to that assigned area. Say about the power and bandwidth. The power and bandwidth of these satellites depends upon the preferred size of the footprint. So it depends on the size of the footprint, then the complexity of the traffic control protocol schemes, and the cost of ground stations. So the responsible for providing these services to the assigned area of on the earth. The satellites work most effectively when the transmissions are focused with a desired area. When the area is focused, then the emissions didn't go outside that designated area, and thus minimizing the interference to the other system. The other thing is the satellite antenna pattern play an important role and must be designed to better cover the designated geographical area. So the design of the antenna is also important. So the satellite should be designed by keeping in mind its usability for short and long term effects throughout its lifetime. So the design should be based upon that, whether you are going to use it for a short term or for a long term. Normally the earth stations should be positioned. See, it's about the earth stations. The earth station should be positioned to control the satellite if it drifts from its orbit, or it is subjected to any kind of drag from the external forces. So that will also happen to the satellite. Sometimes the satellite used to go out of control and it may drift from the actual orbit. Then saying about its application, the satellites are used in weather forecasting, radio and TV broadcasting, used in military and navigation application, for global telephony, and also for connecting remote areas we are using satellites. Next we can go with Kepler's law. In astronomy, Kepler's law of planetary motion are the three scientific laws describing the motion of planets around the sun. Saying about the first law, it's the law of orbits. And about the second law, it's the law of equal areas, and the third law is related to the, you can say it as the law of periods. Saying about the first law, it's applied to any two bodies in space which interact through gravity. So gravitational pull should be there, So you can apply any two bodies in space which interact through gravity. So about the first law, the path followed by a satellite around the primary will be an ellipse. So here you are saying about the satellite and the primary thing. The satellite is related to the secondary thing. The primary will be the Earth. So here the path followed by the secondary thing, the satellite, around the primary thing, maybe the Earth, will be an ellipse. So that is the law of ellipse, the first law. The center of mass of these two body system is termed as barycenter. Is also the center of foci. According to the Kepler's first law, all the planets revolve around the sun in elliptical orbit, having the sun at one of the foci. So when you are comparing the satellite, the Earth with, or the planets with the sun, all the planets revolve around the sun in elliptical orbit, having sun as one of the foci. So here this is the center of ellipse, and this distance is the major axis, and this is the minor axis. So about this from the diagram, the distance A will be half of the major axis. Saying about this point is the barycenter, the center of mass of the two body system is called as the barycenter. This is about the Kepler's first law. Then about Kepler's second law, it's also called as law of equal areas. Law of equal areas. Say about the second law, that is for equal time intervals. Here we are considering the time. For equal time intervals, a satellite will sweep out equal areas in its orbital plane, focused at the barycenter. The focal will be at the barycenter. So the law of equal area says that for equal time interval, a satellite, saying about that, the time interval, time part is very important. Thus, for equal time interval, a satellite will sweep out equal area in its orbital plane. For example, maybe about the sweep here, that is the distance S1 and S2. So this, if the time interval of S1 is equal to S2, it means that the area A1 will be equal to A2. So the area A1 and A2 will be swept out in unit time or equal. That is the second law. And Kepler's third law is called as the law of harmonies, or we can say it as the law of period. So the third law states that the square of the periodic time of orbit is proportional to cube of the mean distance between the two bodies. Or the square of time period of revolution of the planet around the sun in elliptical orbit is directly proportional to cube of its semi-major axis, that is t square. Here the time period of revolution of a planet around the sun, it is proportional to cube of its semi-major axis. That is Kepler's third law. So this law is also called as harmonic law, which states that closest planet travel at the greater speed and having the shortest orbital period. So the closest planets travel at the greater speed. That is Kepler's third law. So this law is purely related to the law of motion. Next thing we have to study in basically in satellite communication is Newton's law. There also Newton has proposed 3 laws, and the first, it is the Newton's first law. It states that an object at rest will remain rest, or it will remain at rest unless acted on by an unbalanced force. Or we can say it as an object at rest will remain at rest unless acted upon by an unbalanced force. This law is often called as the law of inertia. Okay, the first law of Newton's first law is also called as the law of inertia. Say of Newton's second law. Newton's second law is related to the acceleration of a body. So actually Newton's second law of motion describes what happens to the massive body when acted upon by an external force. So it states that the force acting on the body is equal to the product of its mass and acceleration. If greater the amount of force needed, normally greater will be the mass. So greater the mass, the greater the amount of force needed to accelerate it. So that is Newton's second law. And Newton's third law is very simple. For every action, there is an equal and opposite reaction. So it's Newton's third law. So it means that for every force, there is a reaction force. This is equal in size but opposite in direction. That is, it says that whenever an object pushes another object, it gets pushed back into the opposite direction equally hard. That is Newton's third law. For every action, there is an equal and opposite reaction. So these are the two laws, especially the Kepler's law and the Newton's law. So these are the two important laws we are explaining about this satellite communication. Next we can see the orbital parameters. So about orbital parameters, they are very important in the knowledge. First thing, it is apogee. Say apogee is a point from a satellite farthest from the Earth. So or you can say it is a point for a satellite far away from the Earth. So in the diagram, this is apogee. So this is the Earth, and it is the mass center of Earth, or the center of the Earth. So it's a point for a satellite far away from the Earth, and it is denoted as HA. So this is apogee. Next it is perigee, the point for a satellite closest to the Earth. So at this point only, the satellite will be close to the Earth, and it's denoted as HP. Next, the other next parameter is the line of apsides. So it's a line joining. Perigee and apogee through the center of Earth. Okay, so it's the center of the Earth. So line of apsides is the line joining perigee and apogee through the center of the earth. It's the major axis of the orbit. So it's the major axis of the orbit. One half of its length, line's length is the semi-major axis equivalent to satellite mean distance from the earth. So line of apsides. So normally we are considering this as the elliptical path taken by the satellite, or we can say this the satellite orbit. We have seen what is apogee, we have seen what is perigee, and what is line of apside. Simply line of apside is the line joining the apogee and perigee through the center of the earth. So apogee is the farthest distance from the earth for the satellite, and perigee it is the closest point from the earth. And the line joining apogee and perigee is the line of apsides. Then ascending node. So ascending node is the point where the orbit crosses the equatorial plane going from north to south. So here the side is important. So while going from north to south, so it's the point where the orbit crosses the equatorial plane is the ascending node. The opposite will be the descending node, the point where the orbit crossing the equatorial plane going from south to north. So while going from south to north, you will cross the equatorial point. That point is nothing but the descending node. Next is the inclination. It's the angle between the orbital plane and the equatorial plane. So that is the inclination. Okay, the inclination, I, inclination. So this angle between the orbital plane and the Earth's equatorial plane. Okay. Then lines of nodes. So it's the line joining the ascending and descending nodes through the center of the earth. So that is line of nodes. So it's the imaginary line joining the ascending and descending nodes through the center of the earth. It's line of nodes. Next it is the prograde orbit. So an orbit in which satellite move in same direction as the earth's rotation. It's prograde orbit. So the inclination is always between 0 to 90 degree. Many satellites used to follow this path as the earth's velocity make it easy to launch these satellites, the prograde orbit. And the next term it is the retrograde orbit, an orbit in which the satellite moves in the same direction counter to the earth's rotation. So that is retrograde orbit. So retrograde orbit, and this will be the prograde orbit. So in prograde orbit, an orbit is just an orbit in which the satellite moves in same direction as the earth rotates. And prograde orbit is an orbit in which the satellite moves in same direction counter to the earth rotation. Same direction counter to the earth rotation. It is retrograde orbit. The next thing, it is argument of perigee. Argument of perigee denotes omega. It's an angle from the point of perigee measured in the orbital plane of the earth center in the direction of satellite motion. So it's just an angle from the point of perigee. From the point of perigee measured in the orbital plane, So it's orbital plane. So this is the argument of perigee. This is the angle. This is the angle between from the point of perigee measured in the orbital plane of the earth center in the direction of the satellite motion. So it is argument of perigee. Next, it is the orbit argument of perigee. The argument of perigee is defined as the angle within the satellite orbit plane that is measured from the ascending node to the perigee point P along the satellite's travel of direction. Okay, that is argument of perigee. Next is the right ascension of ascending node. The right ascension of ascending node is the angle of the equatorial plane taken from the first point of iris to the ascending node of the orbit. So, it is the right ascension of ascending node. Next is mean anomaly. So, the mean anomaly will give the average value to the angular position of the satellite with reference to the peak. The angle of mean anomaly is measured from the body being orbited in the direction of orbital motion. So, the mean anomaly gives the average value to the angular position of the satellite with refer to the perigee. True anomaly is the angle from the point of perigee to the satellite's position measured at the Earth's center. It is measured at the Earth's center. It is true anomaly. So, it is true anomaly. So, it is the angle from the point of perigee. So, it is the angle from point of perigee to the satellite position measured at the Earth center. So, this measurement is taken at the Earth center. So, mean anomaly and true anomaly. Thank you.